Welcome dear viewers. Today we are discussing the chemistry of transition and inner transition elements. In this module, we are continuing with general characteristic features of the transition elements. These are the transition elements. As we know, there are 4 different series of the transition elements. They are namely 3D series, 4D series, 5D and 6D series of elements. Regarding the general characteristics, it is observed that transition metal have several characteristic features which are entirely different from that of other blocks or other elements in the periodic table. We already came across some characteristic features such as variable oxidation state, complex formation tendency, magnetic properties, formation of compounds, metallic character and alloy formation. Now, we are beginning from catalytic activity of transition elements. Then first case, what is a catalyst? A catalyst is a substance which can alter the rate of a reaction without actually involving in the reaction. A positive catalyst generally enhance the rate of the reaction, whereas a negative catalyst will decrease the rate of the reaction. In many cases, transition metals or their compounds can perform as better catalysts. For instance, nickel can be used as a catalyst for hydrogenation of oils and fats. Hydrogenation means the process of addition of hydrogen towards multiple bond, preferably carbon-carbon double bond or carbon-carbon triple bond. Then iron. Iron is used as a catalyst in the manufacture of ammonia by Haber process. Haber process is the combination of nitrogen and hydrogen to produce ammonia. This reaction is normally happening at high pressure and moderate temperature. This reaction is highly rate enhanced by the presence of spongy iron. Then titanium tetrachloride. Titanium tetrachloride, simply termed as the Ziegler-Natta catalyst, is used for the polymerization of alkenes, which is used in the preparation of several kinds of plastics. Now, vanadium pentoxide. It is a catalyst, salt catalyst. It is a compound of vanadium used in the catalytic conversion of sulfur dioxide to sulfur trioxide for the preparation of sulfuric acid by the contact process. Now, catalytic activity. Catalytic activity is mainly due to 3 reasons. That is, variable oxidation state shown by the transition metals, the presence of free valencies on the surface of the transition metals, and also the ability to form complexes. Next characteristic feature is the formation of interstitial compounds. Transition metals form a number of interstitial compounds. What are interstitial compounds? These are a category of compounds in which small elements like carbon, hydrogen, boron, nitrogen, etc. will occupy the lattice or in the free space of the transition metal. Several examples are reported. For instance, TiC, Mn4n, manganese nitride, Fe3H, TaH2, etc. Special features of interstitial compounds. The interstitial compounds are characterized by the hard nature. They are extremely hard, high melting point compared to the pure metal. They retain their metallic conductivity even in the form of interstitial compound. They are highly chemically inert. Another characteristic feature of transition metal is the formation of non-stoichiometric compound. What do you mean by a stoichiometric compound and how it differs from a non-stoichiometric compound? If you are taking NaCl, here sodium and chlorine present in 1:1 ratio, that ratio is always fixed. In the case of calcium chloride, 1 calcium is connected to 2 chlorine. The stoichiometric ratio between cation and anion is 1:2. However, in the case of non-stoichiometric compounds, the stoichiometric ratio between elements, the participating elements, is not maintained always. Such compounds are called non-stoichiometric compounds. Several non-stoichiometric compounds are formed by transition metal, hence it is another characteristic feature. For instance, titanium forms TiOX. X may vary from 0.65 to 1.25, and for vanadium which forms VOX, here X range from 0.79 to to 1.29. And in this case, it is clear that the value of X is a range. It is not a fixed quantity like CaO, where calcium is connected to one oxygen always. These compounds have a variable composition and formed due to variability in oxidation state and solid defects. See, it should be noted that in the case of the transition metals, there are several defects are present. In the case of some compounds, for example, like NaCl, you are familiar with the defects like a Schottky defect, where equal number of cation and anion will miss from their lattice site. Such kind of defects are also present in transition metal. That solid state defect is a reason by which that transition metal form non-stoichiometric compounds. Now, periodic properties of transition metals. What do you mean by the term periodic property? We are familiar with the arrangement of elements in the periodic table. There are several properties of elements like size of atom, ionization energy, electronegativity, electropositivity, metallic character, non-metallic character, oxidizing power, reducing power, etc. can be related to position of the element in the periodic table. A property which can be related to position of the element in the periodic table is simply termed as the periodic property. Let us have a glimpse on an outlook on various periodic properties associated with the transition metals. First of all, atomic radius. We know atom is spherical. Atomic radius is theoretically the distance from the center of the nucleus to the outermost electron. That is, this is the positive charge center and this is the outermost electron. The theoretical distance from the center of the nucleus to the last electron, this is termed as atomic radius. If we are considering some ions like scandium 2+, then this radius is termed as ionic radius. That is, radius of an atom is called atomic radius, whereas that of an ion is termed as ionic radius. Atomic radius, ionic radius are very important periodic properties. Then atomic radii generally decreases with a few exceptions. Even though some few exceptions are there, the general trend is atomic radius decreases from left to right along a period. This is because of the fact that whenever a new electron enters into a shell, there corresponds a proton added to the nucleus. That is, there corresponds an increase in the nuclear charge. So, for every electron from left to right, there is an increase in the nuclear charge. This nuclear charge tends to attract the outermost electron more close towards itself. Also, the de-shielding effect offered by the d electrons is also very poor, and hence with increase in nuclear charge, there is a strong force of attraction between nucleus and the outermost electron, and the size of the atom tends to decrease as we move from left to right across the period. Variation of atomic radius of 3D series of elements is shown here. From this, it is clear that the leftmost element, that is scandium, is associated with an atomic radius of 144 picometer. We can see a gradual decrease with some anomalies are noted. Yes, here 117 made constant for manganese and iron, then there is a slight decrease, then there is an increase for copper, and up to zinc there is a sudden increase. That is, the values generally decrease along the series up to nickel, then a slight increase for copper, then this increase is pronounced for zinc. That is, from copper to zinc, the atomic radius value increase from 117 to 125. Ionic radii. It is showing similar trend as that of atomic radii. That is, atomic radii also decreases along a period. That is, as we move from left to right across a period, atomic radius show gradual decrease. Ionic radius also show same type of gradual decrease. The ionic radii of transition element follow same trend as in the case of atomic radii. Variation of ionic radii. Ionic radii of divalent cation is different from that of trivalent cation. This chart represents the variation of ionic radii of divalent cation as well as trivalent cation. Whenever we are considering the divalent cations like scandium 2+, titanium 2+, vanadium 2+, etc., we can see a gradual decrease from left to right across the period. In the case of the trivalent cations, there also a corresponding decrease is observed, but the data associated with copper 3 plus and zinc 3 plus is not known experimentally. Atomic oleum. The D block elements have a very low atomic oleum comparatively with the other elements of the periodic table. This is due to the fact that N-1 d subshell are being filled and the increased nuclear charge tends to attract the electron density more towards itself. That is, they occur shrinking. That means there is comparatively lower atomic volume for the transition elements compared to S, P and F block elements of the periodic table. Now another important characteristic feature, that is density. Density can be calculated by using the expression simply density equal to mass by volume. That is, density of an element is the mass per unit volume of that element, and we are discussing the density of the transition elements. Among the transition series, the trend in decrease, the trend in density will be almost reverse that of atomic radius. That is, we learned that atomic radius decreases from left to right across the period, but the density shows nearly opposite trend, that is, density increases from left to right across the period. This chart represents the variation of density of 3D series of elements. Scandium has a density of 3.43 gram per cc, gram per centimeter cube, and for zinc it is 7.1. In the intermittent elements like nickel and copper, the density is comparatively high. This picture represents graphical notation associated with the density. Variation of density. From the picture it is clear that high density is associated with elements like cobalt, nickel and copper. The least density is observed in the case of scandium. Now another feature we are considering here is enthalpy of atomization. This enthalpy of atomization is a deciding factor for many other physical properties like melting point, boiling point, etc. Then what is enthalpy of atomization? It is the enthalpy change. It is defined as the heat change. When a compound's bonds are completely broken and component atoms are reduced to the atomic state. That is, for example, enthalpy of atomization of hydrogen means H2 completely broken into hydrogen atoms and hydrogen still exists in the atomic state. Delta HAT is its notation. Delta HAT of an elemental solid is exactly same as enthalpy of sublimation. Then what is enthalpy of sublimation? Enthalpy of sublimation is defined as the enthalpy change during the conversion of 1 mole of a solid completely into vapor state without passing through the liquid state. That transformation is called sublimation. So in the case of an elemental solid, enthalpy of atomization same as enthalpy of sublimation. Standard enthalpy of atomization represents the enthalpy of atomization when measured under standard conditions such as 298 Kelvin temperature and 1 bar pressure. Enthalpy of atomization is shown here for the 3D series of elements. This data represents the standard enthalpy of atomization. For scandium it is 326 kilojoule per mole. Enthalpy of atomization increases with increase in number of unpaired electrons. Then in the case of manganese there is a decrease. That is, this trend is not a regular trend, but it has a strong connectivity with the number of unpaired electrons present in the transition metal. Enthalpy of atomization generally, on a general way, we can say that enthalpy of atomization increases with increase in number of unpaired electrons. It is an important factor that I already mentioned, depends on several other features like melting point, boiling point, standard electrode potential, etc. of a metal. Metals with very high enthalpy of atomization tends to be inert. That means from the metallic solid it is too difficult to separate them into atomic level such that the possibility to undergo chemical reaction will be very low. That the metals with very high enthalpy of atomization is behaving like an inert material. The enthalpy of atomization is directly proportional to the boiling point. Now, the melting and boiling point of transition metals. their melting and boiling points are comparatively very high. We are familiar with the tungsten, the transition metal with the very high melting point used in the preparation of the bulbs as the filaments. Some metals with their melting point are shown here. The melting point is given in degree Celsius, and from this it is clear that scandium having 1540, but for the first transition series most of them are above 1000 degrees Celsius. But see the case of the zinc. In the case of zinc, it is this melting point is only 420 degrees Celsius. What is the reason for this very high melting point associated with the transition metal? The reason is simple. In the case of transition metal, electrons from n-1 d subshell and ns subshell are involved in chemical bonding. The chemical bond present in the case of a metallic solid is called metallic bonding. So, the number of electrons available for metallic bonding is higher in the case of transition metal, hence its melting point is high. Boiling point also show a corresponding high value. This is graphical representation of the melting point. From the picture, from the graph, it is clear that high melting point is associated with vanadium and chromium. For zinc, the value is comparatively very low. Zinc, due to its D10 arrangement, its properties are entirely different from that of other transition metals of the same series. Now, another important characteristic feature of transition metal, that is ionization enthalpy. What do you mean by the term ionization enthalpy? The amount of energy required to remove the most loosely bound electron from an isolated gaseous atom. Suppose I wish to convert sodium metal to sodium ion. That is, I have to remove one electron from sodium to get Na plus. The energy that I have to supply for that conversion, for the removal of the electron, for the removal of the outermost electron under standard condition, that is under gaseous condition, is known as ionization enthalpy. Regarding the ionization enthalpy of the transition metals, these ionization enthalpy values are fairly high or comparatively high, and these ionization enthalpy values of d block elements or transition elements lie in between the highly reactive metals S block elements and that of P block elements. Thus, we can simply say that the ionization enthalpy values of the transition elements are between that of metals as well as non-metals, or between S and P block elements. The ionization enthalpy of transition elements increase, but very slowly, but very gradually from left to right across a period. The reason is because from left to right across a period, there is a decrease in the size of the atom or decrease in atomic radii. The ionization enthalpy of 5D series are higher than that of 3D and 4D series of elements. This is due to the presence of poor shielding effect offered by the 4 of electrons. The ionization energy values of 3D series of elements are shown here, and in this chart there is first, second, third and fourth ionization energy. Then what is the difference between first, second, third and fourth ionization energy? If I am having a metal M, I wish to convert it to M plus by removing one electron. The energy required for this purpose is termed as first ionization enthalpy. If I wish to convert M plus to M2 plus by removing one more electron, then the energy term involved is called second ionization enthalpy. Similarly, if I wish to convert M2 plus to M3 plus, again by removing one electron, the energy term involved is called third ionization enthalpy. It is a general trend that first ionization enthalpy is the least. First ionization enthalpy less than, second ionization enthalpy less than, like that. What is the reason why this increase? That is, consequently, if you are removing electrons, you are always generating a positive ion. It is too tough to remove an electron from a positive ion rather than from a neutral atom. That is, whenever we are considering several consequent ionization energies, least value is observed for the first ionization enthalpy. In the case of 3D series of elements, we can see the regular trend. First ionization enthalpy, let us take the case of the scandium. Here, the first ionization enthalpy is 632 kilojoule per mole, but the second ionization enthalpy is nearly 2 times that of the first ionization enthalpy. So, there is increase and the fourth ionization enthalpy being very high. Some anomalies are also reported. That anomalies we will discuss. That anomalies mainly arise due to electronic arrangement, stable electronic configuration. Any metal system will not wish to disturb its stable electronic configuration. The first ionization energy values of the 3D series of elements show some irregularities or some irregular trend, whereas the second and higher ionization enthalpy show a regular trend, regular increasing trend. But in the case of zinc, we can see that the first ionization energy is comparatively very high. The very high value of first ionization enthalpy of zinc is attributed to its stable electronic configuration. That is, for zinc, the electronic arrangement is 3D10-4s2. This is a very stable electronic arrangement. It is completely filled in the case of 4s as well as in the case of 3D10. So, whenever I wish to convert zinc to zinc 2 plus or zinc 3 plus or any other higher states, we are disturbing this stable electronic arrangement. Every metal prefers to have some stable arrangement always. Therefore, disturbing that stable arrangement require more energy. High ionization enthalpy associated with metallic zinc is due to its stable electronic arrangement. Then, the variation of ionization enthalpy along the series mainly due to the change or decrease in atomic radii, and this atomic radii decrease is attributed to increase in nuclear charge as well as the screening effect offered by the intervening electrons. The second ionization enthalpy show usually high values for chromium and copper. What is the reason? It can also be connected to stable electronic arrangement. That is, whenever I am taking chromium, we have the electronic configuration 3D5-4s1. For copper, the electronic configuration is 3D10-4s1. Thus, for Cr plus, the arrangement is 3D5. This is a stable arrangement. For Cu plus, the arrangement is 3D10. This is again a stable arrangement. That is, you can easily convert the chromium to chromium plus. Also convert easily copper to copper plus. This is first ionization energy. This is also first ionization energy. That is, the first ionization energy of chromium as well as copper is comparatively low. But we can take the second ionization energy. Suppose I wish to convert Cr plus to Cr2 plus. The new configuration will be 3D4. And when copper plus is converted to copper 2 plus, the configuration will be 3D9. So, this conversion is the conversion from a more stable electronic arrangement to a highly unstable electronic arrangement. So, the energy required for this is very, very high. That is, the second ionization energy will be very high compared to first in the case of chromium. Similar case is observed for copper. Whenever you are converting copper to copper 2 plus, you are disturbing the electronic arrangement 3D10 and convert it to a more unstable arrangement of 3D9. For that, you have to provide very high energy. That is, for the elements copper and chromium, second ionization energy value will be very high compared to the first ionization energy value. Another important characteristic feature of the transition metals is their electrode potential. We are familiar with the electrode potential measurements in electrochemistry. Electrode potential may be reduction potential or oxidation potential. The tendency of a metal ion to get reduced is expressed in terms of volts, then we can call it as reduction potential. Similarly, the tendency of a metal to get oxidized to cations is expressed in terms of oxidation potential. That means oxidation potential and reduction potential are equal in magnitude but opposite in sign. As per IUPAC recommendation, reduction potential is simply taken as the standard, and standard electrode potential of the 3D series of metals for the conversion metal 2 plus 2 electron to get to metal is shown here. That is, in this chart we are representing the tendency for the conversion of divalent cation into a neutral metal atom. The electrode potential shows some negative sign except for one metal, that is copper, where the reduction potential is positive. Reduction potential negative means the tendency to get reduced is minimum. That means the metals have higher tendency to get oxidized. Metals are electropositive and hence they are associated with high oxidation potential values. That means they have low reduction potential values. That is correct in the case of all metals except copper. For scandium it is minus 2.10, for titanium minus 1.60, some variation can be observed. Thus in the case of copper, the conversion of copper 2 plus to copper is a very favorable process. That means copper has a greater tendency to get reduced, whereas other metals have a greater tendency to get oxidized. Thus, the standard reduction potentials of the elements of 3D series except copper are lower than that of standard hydrogen electrode. For standard hydrogen, the reduction potential is taken as 0. So, these metals except copper have negative values, means less than electrode potential of standard hydrogen electrode. These elements except copper can liberate hydrogen gas from dilute acids. That is, when these metals scandium, titanium, vanadium, chromium or manganese or iron except copper placed in dilute acid, liberation of hydrogen gas will happen, because metal will undergo oxidation, at the same time H plus undergo reduction to produce hydrogen gas. But copper cannot liberate hydrogen from dilute acids, because copper always tends to reduce when compared to hydrogen. The trends in standard electrode potential that we just went through the last slide is shown here in the graphical form, and for this one represents that of copper, where one and only positive value is observed for the reduction potential of divalent cation. That is, copper has tendency to get reduced, all others have a tendency, more tendency to get oxidized. That is, copper cannot react with acid to liberate hydrogen gas. This represents the trends in reduction potential, standard reduction potential for the conversion of metal 3 plus ion to metal 2 plus ion. That is, the trends in reduction potential for the conversion of trivalent cation to divalent cation is shown here, and that tendency, some elements have positive charge, some elements have positive values of reduction potential, some others have negative values. Yes, the values show some variation trends or some varying trend. This varying trend is definitely attributed to stable electronic arrangement. For example, the comparatively high value of manganese shows that Mn2 plus is particularly stable. Let us take the case of manganese, and this plus 1.57 value simply indicate that manganese is now present in plus 3 state, and we are measuring the conversion possibility. Mn3 plus 1 electron gives Mn2 plus. This conversion possibility is very high because its value is plus 1.57. This high value of reduction potential represents this reduction is a highly favorable process, and this is attributed to stable electronic arrangement. For manganese 3 plus, the electronic configuration is 3d4, but for manganese 2 plus, the electronic arrangement is 3d5. Comparing 3d4 and 3d5, it is observed that 3d5 is a half-filled configuration which is highly stable. So, manganese 3 plus as such has a high tendency to get reduced to Mn2 plus. That is why Mn3 plus to Mn2 plus reduction potential value is a high positive value. Reducing power is inversely proportional to reduction potential. What do you mean by the term reducing power? Transition metals can reduce some other metals or some other compounds. The power to reduce from higher oxidation state to lower oxidation state is simply termed as reducing power. The reducing power is connected to reduction potential. Reducing agent always undergo oxidation. That is, for good reducing agents, the oxidation potential must be very high. If oxidation potential is very high, reduction potential will be very low. That is, we can ultimately speak that the reducing power of transition metals inversely proportional to reduction potential. That is, higher the reduction potential, lower will be the reducing power, and vice versa. Thus, the reducing power of transition metal inversely related to reduction potential. That is, higher the reduction potential, lower will be the reducing power, and vice versa. Thus, in this module, we have discussed several characteristic features like variation in periodic properties, their reduction potential values, ionization enthalpies, etc. Thus, we have discussed all the characteristic features of transition metals. That's all about this presentation. Thank you.